I think it is okay. Now is out. Everything is out. Good. Everything is good. I'm on live already. And I see that there is a certain number of students online, participating online. Yeah, yeah, and it's a time, about the time to get started too. So let me close this one. I don't know where this eventually went. It was somehow disappeared. Okay, and then, oh yeah, this one. That's the last thing to do. So which one it is streaming now? HDMI. Should I use something here?
No, I think it says with the remote.
Control panel is not working. Use remote control to PC to laptop. So there's a. Can you find it?
Over here there it says only video and computer. So computer 2 will be, I guess that press computer 2.
This is computer one. What about this one? What about video? Okay, so we are almost good to go. The one thing that is missing is that we are not able to display anything to this overhead projector. But as soon as that's done, then we can go. Okay, let me check. No, I don't think it is this. It was working, but as soon as I put that on, then was not willing to work anymore. So let me see if I do this. Because I see that this is blinking now. It is blinking, but still no. Another blink. Now it disappeared completely. Duplicate.
It should is option duplicate.
How come it's not? The one thing that I can do too is that I can use this display, this one, but it's going to be with a quite serious delay.
Turn it off and turn it on again.
On, off. No, he's not even willing to turn it off anymore. Okay, and on. So look at that. Somebody started to make a note to this whiteboard. Another one here. Okay, still nothing.
I think if it won't work, we just change the
You
inputs.
think that we should touch that?
Yeah, because at the moment this is input number 2.
Okay. How about the camera-wise? Is it? I think it is okay. Yeah, this is it's, here. This is good. This is the best. Yeah. All right, so we get started. Right. So we're gonna get started as soon as I'm able to display something to you guys. The online participants are already able to see it, but it's gonna be a bit inconvenient if you guys gonna take a look at the slides through your phone. Okay. How come it's still nothing here? Okay, now the same thing came here. Computer one, no input. Computer one, no input.
Computer 2.
This is computer two, no input. Okay, one more video. No input. Yeah, please do, please do. And I'm gonna put it back to the video computer one. So this is computer one.
Because it says you have inputs in signal 1 and 2.
Yeah, and it was on. It was already on a little while ago. The last thing that I can do is that I can switch off this computer, this one. What do you think about
But
that?
you are actually streaming.
But I don't think the streaming is not going to be discontinued.
Think so?
Yeah, I don't think so. Because it was already on when we started. Okay, I'm going to take it off. Oh, what the heck is this? All right, and then I'm going to lock off. Was this lock off or?
Switch it off.
But let's try this one first. Because this was a computer was on. Okay, it was like exactly like this. And then what we did was we did this one. So we connected like this. And then let's try extend. How the heck is this not working? So what this says? What this says? This is a HDMI in. You got it. Okay. Hold on, hold on. My cable is disconnected.
Switch on even the camera, even the other computer. It's fine.
Okay. So I can log in here.
So now this is your computer.
Fantastic. So what I'm going to do is that I'm going to just duplicate this one. Okay, great, 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 great. So the last thing that I'm going to do is that I'm going to put myself back to the YouTube here so I can see the comments from online participants.
So far,
David, would like to be a YouTube officer this time too?
Sure.
Okay, so can you check if there's any comments, questions from online participants?
so far it hasn't been anything.
Great, great. All right, I think we get ready to get started. Now, let me just, the last thing to do is that I'm going to put the YouTube on such that I can see what's going on in a YouTube channel. Okay, guys, we're going to close today at 11:45. All right. Your channel. Okay, I see that. Okay, I got 2 likes, no comments. Perfect. Thank you, guys. Like I say, I'm going to close today at 11:45. Hey, before you go, guys, so can I introduce you? Well, you already know you already know Mustafa, you already know Suraj, but just to make sure that, if there's anyone not participating, I did not participate in a class in the last fall semester, the teachers are here. So Greg, you're going to see a bit later. He is the guy that will be responsible of this AI part of the class. How that's going to be handled, I will explain that to you momentarily. And then Suraj, Dr. Suraj is here. So would you like to stop by in a camera? And he's looking pretty like that. And then the Mustafa is our strong guy. Look at these guns. Oh my God. So the guns all arrived to city. All right, so these are the teachers, and then of course me, and I hope you know me. So it's Aki. So please call me Aki. All right, so that's about it. So 11:45. So we're gonna close at 11:45. Thank you, guys. All right, very good. Okay, welcome to class. And as promised, I said in December, if I remember correctly, or November, that this course is the best course that the university can offer to you. So now there's a big promise that I need to deliver to make sure that you're smiling all the time. In every single lecture, you're smiling. In tutorials, you're smiling as well, and so on and so forth. We'll see if I'm able to do so. But the subject-wise, this is way more pleasant than the course we did in fall semester. And why is that? Because the fall semester was very theoretical. It was about the partial differentiation, partial this, partial that, Jacobian, Lagrange multipliers, virtual displacement, so on and so forth. That was involving, very, very complicated, very theoretical. Some of the concepts were painfully complicated. What we're going to discuss this class is more hands-on. This is how you can use a simulation. These are the kind of the concepts that make sense to use. Use this, don't use that. And then the big new part of the class will be related to how to use artificial intelligence. So we're going to have a different subject matters related to artificial intelligence, because artificial intelligence, that too is a very broad area, super broad area. And I would like you to be aware of the certain things. You're not going to be master of all the details, but at least you're aware of the certain recent developments and how they impact, how they will make a major effect to your engineering life. So, and then of course, then there is a really hands-on work that you need to do. There's a simulation work that you need to do. But this class is having the same idea that in a simulation of mechatronic machine, in the sense that we are looking the mechanical components that are combined with the actuators, that are then combined with the control system, that is they may be operated by human. This whole concept will be more, put it in a more alive, this class, a more practical scale. Okay, that also, I don't know if I should, but I still gonna do this. There's gonna be another few discussion about the career counseling. So we started last semester, we discussed about master thesis topic, but then there's many other things to discuss, career counseling wise. How to find a position, how is the life in academia? If you wanted to find a position in the industry, what makes sense to do? And it becomes to be quite critical time, because at this time of the year, there is already quite a bit of position openings in industry and in university. And these position openings are mostly for upcoming summer. So industry is actually looking for, new ideas, new people. And the best way that they will get the new people is that they hire a person as a summer employee as a beginning. And right now, right this time, is the time to make an application. And make sure that you submitted a lot of applications. And also, I don't know if you recognize this, but there is a position openings in university too. I noticed that one of these televisions that you can see in the corridor, it was mentioned that please apply to be a summer employee. And please apply. Because if not applying, you're not going to get the position. They will not force you, they're not going to twist your hand and forcing you to work for university and say for companies. That's not going to happen. So you need to be the one that is initiating the process. I think that I need to do this quite fast, because deadline for this summer position is, so when is it? End of January. Okay, that's for university. What about the companies?
Also.
Same.
Maybe 5th February. Very few closes in 31st of January. Most of them closes in the mid of February.
All right. So let me think. I might need to do this already next week. So I'm going to make a short sidestep from the technical subject matters about the career counseling. I don't know why I feel there's a big pressure in my chest that I wanted to explain stuff related to career counseling. Like it or not. Of course, you can skip the lecture if you don't like it, because it's not going to be anything related to exam, but something that I wanted to share with you. And it's going to be next week already, because of the deadlines. I wasn't aware that the deadlines are coming that fast. Okay, all right. Anyways, so what else? What else can happen is this. Well, you learn the teachers already. And the best way, by the way, to get touch bases with the teachers is to send an email. Of course, you can set this meeting as well, but easier is first send an email and say, hey, Aki, do you have time to meet me? And I do. I always do. Because I'm for you guys. All right, so this is what we're going to do in this class. So we're going to learn to use simulation as a part of the product development process. And not necessarily just the product development, but more about, in the different product processes. But the simulation assignment you're going to do in this course is more about product development. How you can make better products based on simulation. How is it the simulation can help you to look at the things that otherwise would be complicated to do. So that's what we're going to do in the very beginning. And we're going to discuss about three-dimensional models. So this course is all about the three-dimensional models. So in a previous course, we discussed about the planar models. Not anymore. So we're going to move on to space, and we're going to think about how is the spatial cases. And it's going to be continuously like that. And it means that we also need to revisit in the kinematics. Remember, in our very beginning when we met, and that was September, we started from the kinematics of the particle and everything was in a planar. But now we're going to do the same, short revisiting, but we're going to take a look. What makes things different if everything is in a spatial case? So that's what's going to happen. And then another thing that is going to be new technical information is flexible bodies. So what if body is not assumed to be rigid? Remember, we make this big assumption that regardless of the forces, the body will not deform. And in reality, it's always deforming. Sometimes the deformation is so significant that it makes a major impact to dynamic responses. Okay, what if that's the case? How is that we can model deformable bodies? This is something that is my favorite subject matter to explain because it takes us to make a short introduction to finite element modeling. Finite element modeling is one of the fundamentals in engineering analysis. It's one of the most often used analyzing method, to be more specific. How that is, what that is based on, and what are the assumptions, how that works, and how that can be used. I want to make a short introduction in that subject matter. It's my understanding that you guys already know the finite element method. So you have heard about it. You have used it because there's plenty of commercial software how to use it. So, but we're going to take a look at the background, a little bit about the theoretical aspects. Not too heavily, but a little bit in that direction. And then comes the big thing, how finite element models can be used as a part of the dynamic analysis. Because my understanding that most often, when you learn to use a finite element modeling, you use it in a static cases. Static strength of structure analysis, seeing how much is a deformation, how much is a stress and strains, which is a very natural way to use a finite element method. But here we want to take that in another level, and we wanted to use that as a part of the dynamic analysis. All right, so that's what's going to happen. And then, of course, the big thing is what is the relation between the simulation model and reality? Because it's not the same thing. They can be close to each other, but they're never the same thing. And how is it, again, we can develop the critical thinking against simulation. Remember, I explained that there is this very severe medical condition, simulation disease. Very bad, very bad. And the simulation disease means that you are not using your brains anymore, but every single thing is based on the complicated, very, very complicated simulation model. Here's an example. Sometimes you give an assignment to your student that, okay, why don't you compare the deformation of a cantilever beam and a cantilever beam? World is full of the pre-calculated tables to compute the deformation of cantilever beam. But instead of using these pre-calculated tables, which gives the solution just like that, they decided to make very complicated finite element model, and based on the finite element model, they even computed things incorrectly. This is a very bad symptoms of simulation disease. no medication. You cannot, if you're going to get it, it's going to be a hard recovery process to get rid of that. Okay, we're going to discuss about that. And then different simulation approaches. We're going to look at a little bit about the gamification aspects. We're going to look about the contact modelings. We're going to look about the smooth, non-smooth dynamics. And this is something that is related to contacts. We haven't discussed about much of the contacts, but if you think about the simulation models in practical cases, very, very often there's a contacts, one way or another. So the bodies are colliding, there could be particles that are colliding. How is these collisions? How is this contacts can be described? And then there's two different lines to select. There's a smooth dynamics and non-smooth dynamics. What the heck they mean, how they're different, that you're going to learn later this class. All right, and then another simulation things too. And then the understanding basic of artificial intelligence technology, large language models. That's ChatGPT is one example of that. But there are many, many other software tools similar than ChatGPT, and how those can be used and how they can be, how you can actually make something productive out of it. And I think you need to be aware of it because and maybe you're already very good in that. Maybe you're already making all your reports using ChatGPT. I don't know. But something that we can explain you how to be clever with large language models. And then we're going to look at the surrogate models, data-driven models, AI-based control schemes. So that's going to be quite a bit of things to do. It's going to be something that will be organized in terms of AI workshops. First time we do this. So it's unclear how successful it's going to be. But we are very excited. So Greg will be the one that is primary responsible of that. And of course, just make sure that you understand, the correct name is not Greg, but Greg's name is we call him Greg because his real name is a little hard to pronounce. You can give a shot if you want. Okay, so what is Greg's real name? So that's the first assignment. Gregorsk. Okay, and then the last name is Orzehovskis. All right, so AKA Greg. Okay, but when I say Greg, it means Greg. Okay, all right, you got it. Good. Okay, so we were here. All right. Then, like I say, the overview of modern simulation approaches. And we're going to take a look at the vehicle modeling, contact modeling, finite element, so on and so forth. And we're going to hopefully get a lot of visiting lecturers. So you will get the hands-on information about vehicle modeling, what it means. I'm hoping to get the professor from Tampere University to explain about railroad dynamics, which is a very exciting thing. And when listening to that lecture, it's a miracle that the trains are running between the Lappeenranta and Helsinki, and they actually don't run well, particularly at this weather condition. But the way what this railroad dynamics is, how railroads are based on, and how that can be analyzed, you're going to learn a bit later this class. And other highlights about different areas. So you will get more about practical information about many different applications. Okay, how this sounds like? That is okay. So we'll see. Anything you wish to learn more? We also have these traditional bicycle dynamics. So I don't know if you wanted to hear that or not. This is, something that is quite interesting too. But anyways, we get back to this as soon as we're proceeding in the class. Okay, contact, lectures, workshops, and one simulation work. And the one simulation work is a simple mechanism that is modeled using deformable body. One body, which is a lift arm of that 1 degrees of freedom hydraulic driven crane. This lift arm is going to be described as a flexible body. That's going to be the one practical simulation assignment that you need to do. AI workshops are giving you help. In certain perspective, they're giving you help to do this modeling, but it's more about more broader perspective, how the large language models can be used to create models, how they can be, because you can actually use them to create even the multi-body models. You can go to ChatGPT and say, hey, create me a 4-bar mechanism using this and this software code, and the 4-bar mechanism is coming with this and this dimensions, and it goes pretty much correctly most of the cases. Not very complicated cases, but most of the cases it can do the model for you. And it's something that there is a prediction that is going to change life in engineering quite a bit, because the mechanical engineering work can be replaced by large language models. And you guys need to be aware of this. Okay. Right, so hydraulically driven thing. So it's going to be flexible mechanism. So it's going to be model verification and designing of control scheme. So that's what's going to happen. And this is going to be the subject matter of a guided tutorials. So tutorials is all about how to do this simulation work. And the teaching goes in such the way that I'm going to get started today with 3D multi-body system dynamics. So I'm going to, like promised, I'm going to revisit in kinematics. We are not going to tell the whole story like it went from all these details about virtual displacement and so on and so forth, but we're going to simply look at the kinematics, and then I trust the rest you can do by yourself if you want, because rest will be exactly the same than in a planar case. And then comes flexible bodies and finite element modeling, and then week 6, 7, and 8 will be altogether about AI workshops. So this is something that if you have a hard time to participate, you should let us know in advance, because that's going to be a physical computer class meeting where we're going to do assignments together. This is how you can get this package to do this and that. This is how you can control your model based on the AI. So rather than explaining the theory, because the theory will be so complicated that it's going to be painful, and you're not going to gain much if you know the theory of large language models. I mean, it's maybe beneficial, but more beneficial is that you can use it. And this course is more using than knowing the theory. Knowing the theory a little bit about context and so on and so forth. Okay, and the midterm exam. By the way, midterm exam will be organized in such that every single subject matter that I'm about to explain, it gets started by first saying, these are the possible questions. And I'm going to give you a promise. I will stick on those questions. So I will give you a list of questions that I can ask, and nothing but those questions. And then before the midterm exam, there is a voting action. So you can select one question that you hated the most. And we're going to take it off from the list. So you don't need to worry about that. So it's going to be taken away. And the one question that you like the most, and the one you like the most will be in 100% certainty will be an exam paper. So you can prepare yourself, because it's going to be there for sure. Okay? And the one that will not be there, no matter what. I can love it as much as I want, and if you hate it, it's going to go away. Okay? Is that fair enough?
Very good, actually.
Yeah, very fair. Because this is all about learning, really learning. So I don't want to make you, and also I know that you guys are busy, you have many things to do. And, I need to respect that you guys are busy. I'm not that busy person, so, I need to respect your time stable. So that's how we're going to do. Okay?
That's very small, actually.
Yeah, okay.
Thank you.
Yeah, so I'm going to show you an example momentarily. This is what I'll be planning. But, there's railroad dynamics not mentioned here. That's not decided yet, but I'm hoping it's going to be there. So biomechanics, gamification, large deformation. But I'm hoping to get more visiting lectures, because I really like this, even myself. I like these visiting lectures. They give you a nice, different viewpoint about things. Particularly this railroad would be something that I did not thought about it carefully enough. But anyways, so this is how it goes. So this is tutorials, and there's going to be midterm report. So we're hoping you to get started with the reporting, to show you the way that it's like exercising or helping you to put yourself in a mindset that is needed in when you do your master thesis work. So in your master thesis work, one of the most critical things that defines your success is that how you get started with your writing process. Here we're gonna practice in that. So as soon as you initiate the project, you also initiate the writing. And that's why we have these midterm reports here. So you need to deliver it on those on timely matter.
Excuse me, there's a question.
Okay,
Are the exams on Moodle or physical?
model. Model. So, so there's going to be, again, it's going to be model, but it's going to be a certain time when we're going to organize it. But I don't want you to be in any of the exam rooms because you guys, this is something. This actually came during the COVID time. That because during the COVID time, the exams, physical exams, were not possible. So then we organized in Moodle, and I know that there's this possibility you guys can cheat, but who is losing if you do the cheating? It's definitely not going to be me, but it's you. So, so go easy with that because really, what I'm asking you to learn is not that much. It's not going to be that much. And the midterm exam is not going to be that significant player in your entire grading. But let's look at the grading momentarily. I think at this slide. Okay, here it comes. So the grading goes such the way that I have three components. And the three components that this grading is based on, actually it's 4 components, but maybe easier to consider as 3 components. Except that simulation work is going to be 1/3 of the final grading. Then there's optional workshops. So simulation work is a mandatory, so you need to do that. If you're busy, if you don't find a way to participate in this AI workshop, skip it. That's okay. You can still score high from this class, very high actually. And then written examination or 2 midterm exams, which I recommend heavily. That is going to be 2 midterm exams. That's going to be 1/3. And then one additional component is in-class quizzes, which is a total of 2 points. 17 points divided by 3. 5 is max. 5 is still max. Because theoretically you can get 6 because we're always rounding up. But student affairs office, they don't like this joke. If I can give you 6 out of 5, they're not going to like it. So that's how it goes. So you can do the math. You can practice out, what are the ways to go. If you're scoring 3 from written exam, and then simulation work could be another 3, then you skip the AR workshop and you've got the English in-class quizzes at 2 points. It's going to be 8 points divided by 3. It's going to be 3 as your final grading. As an example. All right. So lectures are on Wednesdays, well, like today. And then, then there is a Suras. So this more information about the tutorials will be available a bit later. So this is something where we were putting together slides together. Suraj did not notice this, check this. But anyway, so he's going to give you more information about the tutorials, and that's going to be via Moodle website. Okay, no mandatory participation. So if you're busy, then you don't come. If you want to skip the lectures, you skip the lectures. And if you're not able to participate in the tutorials, you don't do that, but you are the one that will face the consequences. Clear? Fair deal. All right, good. All right. Here are the in-class quizzes. So it's a total of 25 points. And, this is incorrect. So it's going to be, so this one here is going to be, if you're scoring more than 14 points, I'm going to give you 2 extra points in your final grading. 2 extra points. So you don't need to score every single question correctly. But 14 out of 25, meaning that some of the classes you can skip. You don't need to participate. So it's quite mild. I would say pretty mild. All right. So if you want to, and it's possible that, you must do this simulation assignment that we discussed earlier. You also need to make sure that you are handing over the midterm report timely manner. If not, we're going to take something off from your final number. Each time you miss the deadline, we're going to take half a point off. These are the these mid reports. All right? So half a point will be reduced every time you miss it. So you can miss it, but then your maximum grade will come down quite a bit. And this is what we are gently forcing you to get started in a timely manner. Because we know that what's going to happen is that you're thinking, oh, this is, I can have a laid back attitude and everything's going to be pleasant and nice. And then we are approaching end of the beginning of the May. And then there's a deadline for every single course and you will be overwhelmed. And then you're asking, okay, there's so much work, so many deadlines. I cannot survive. I need to get an extension. And it's going to make our life difficult too. Okay. And then the final deadline, that's really, really hard. So if you miss that, then we're going to divide whatever points is left by 2. Okay, so with, let's say that I think there's a total of 4 times that you need to deliver a mid report. You miss them all. So maximum is going to be 3. And you miss the final deadline. So your maximum is 1.2, 1.5. So it's 2. We're going to round it up for 2.
You get a 1. Would you still get a 1?
You can still get a 1. You can still pass the course. But it's not going to be great. You're not going to score very high anymore. But you can still pass the course, which is important for us and for you. Because then we don't see you anymore in the next year class, which is great. And you will proceed in the direction of your master degree. So win-win. What do you think? Okay?
It would be crazy enough to miss the classes.
Yeah. Well, because you can be busy. I know that you're busy because you're busy people.
This is critical as well.
Yeah, but I know that you have also a lot of other responsibilities like making big parties, traveling to Lapland, because the Lapland is, I know that it's about time to go to Lapland. The student union is every single year organizing the field trip to Lapland. So when is going to be this year? Is it going to be?
They haven't issued the leaflets yet. But
Okay, but it's going to be soon, which is great because Lapland is going to be colder than here, darker than here, because here is too warm, too pleasant. So you can go to Lapland to experience some extremely cold weather. How that sounds? But it's very popular. Many students are going, and then there's this story that I cannot come. You cannot come. You cannot come. We trust that you're busy. So you're the one that is mastering your calendar. Okay. All right. So these are okay, I'm sorry. So it was 3 midterm reports. So the final report. So if you miss the midterm reports, then it's 3.5. That is divided by 2. So it's going to be 2 is your max.
Is there going to be Ekra?
Is there going to be?
Is there going to be Sunday on week 5? Or?
Yeah, that's going to be explained by Suraj, but it's always a Sunday. I think actually, let me correct that. It might be Friday too. We wanted to keep it Friday because that's going to be something that you can give a more pleasant weekend. I know that.
The problem is we have on Thursday.
Yeah, I know that you guys are working every single day, but it still would be nice if you can submit it on Friday. So then at least Friday, Saturday, perhaps you can take it easy. That sounds good to me.
Basically, this is our homework.
Yeah. Okay. All right. Previous knowledge. There was something in the previous knowledge last year, but I took it away because what you need is can-do attitude. That is the most important thing because you have the can-do attitude, we can do the rest. So we can do the rest together. If you don't have a can-do attitude, there's nothing we can do to help you. It's not going to be possible to pass the course. Simple game, can-do attitude. Okay. All right, literature, there's a PowerPoint present, PowerPoint material, other material available in Moodle. And then my professor's book, so Ahmed Shabana's book. It's not going to be easy to reading. It's not going to be easy reading stuff, but it's something that you might consider to borrow. You might consider to browse it over. But again, if you're busy, I understand you don't do that. Yeah. Okay. 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 Then there's this book. There's a lot of different versions out there. Edition 6, I think it is the latest. Doesn't really matter which one you select because every single one is more or less the same material. Particular chapters 5 and 6, they don't change. They did not change that much, but it's one of the fundamentals in a multibody, and that's why people keep on purchasing it, and that's why the new editions are needed every now and then. But the new editions, there is always something new on it, but again, this particular chapter is pretty much all the time same. All right, I promised to Suraj and Mustafa we're going to close today at 11:45. I'm going to use 5 minutes to introduction, and then I'm going to dive into the 3D multibody. 3D multibody is something that you already are familiar with at a certain level because you know this method based on Euler angles. But Euler angles are not heavily used, at least in the modern computers. They are not used at all because they're suffering from mathematical drawbacks, which is the singularity. Actually, every method that is based on 3 parameters always suffering from singularity one way or another. So we're going to discuss about something that is based on 4 parameters. And that's going to be the main body of today's lecture. So describing rotation using 4 parameters. Very confusing because the body can rotate how many different ways? 3 ways. 3 ways. How come we need 4 parameters to describe 3 ways? Something is not matching here. Something is off. But something that is needed to make this happen. This is mathematically very fluent and I kind of give you an idea that, this thing that is obviously simple, body rotation, is mathematically still very involved, not simple. Okay, all right. But what I will learn from this course. So what you're going to learn from this course is, of course, that you can learn to combine different things. Combination is the key. We're going to combine finite element models. We're going to combine control schemes, and we're going to combine even the CAD models. That you can make a CAD model and you can bring it to the model such that it looks realistic, and not just the look, but also the inertia properties will be correct because they're coming from the model that is good representation how things are in reality. So combination of things, that's extremely important. Multi-body system dynamics, finite element modeling, hydraulics, control algorithm, GATT, contact modeling, so on and so forth. Combination. It's a mix of things. That's what we wanted to do. And more like doing rather than learning the theory. I mean, we do learn the theory because I cannot help myself. I need to explain about this smooth, non-smooth dynamics. And but then we also put the main emphasis on doing rather than theory. Okay, so this is how it goes. And then, of course, flexible bodies. There's an animation that this. We're gonna take a look at this. The story we touched a little bit about in a first class. How to describe large deformation. How is that we can take the multibody to cases that are very, very challenging. So we're looking a little bit at special things about how to describe large deformations like belt that is in your engine, and how to describe this small deformation cases that we're going to learn in the beginning, but we're going to take a look what is that you can expect to see in the near future. And something like cable, the wire modeling that you can see in this animation, I don't think we're going to really discuss that so much, but a little bit of special cases here and there, because pretty much everything can be modeled, pretty much everything. It's just that the certain cases that are so complicated that you need to invest a serious time and effort to make it happen. Okay, so that's what this course is about. And then something that is takes me back to the 100 years in history, takes 100 years back in the history. So at the time when I was young. So my doctoral dissertation was about fatigue and how to use a multi-body system dynamics as a part of the tool to make predictions about the fatigue failure. We're gonna go and take a look at that because it's still a valid story today. And it's a valid story because there's a big trend at the moment that the companies would like to use high-strength steel more than ever. High-strength steel. And the real reason for that is that they would like to make structures to be as lightweight as possible. And the one possibility is to select the material to have a better properties than, let's say, conventional steel. High-strength steel is the one possibility. Elastic modulus is going to be still same, regardless of how high-strength your steel material is. And that means that structures will be more slender. They will be more flexible because they can handle higher stresses. So they can be bended. I need to be careful because I have remember these big muscles, so they easily can break this easily. Okay. Now, if you use a conventional steel, the deformation may be this much. But when you use a high-strength steel, it could be like this much. Okay, then there's going to be a big problem. And the big problem is that, first of all, you need to be able to control the dynamics. The dynamics is going to be more involving. And already some of the applications, structures are so flexible that the flexibility itself is a major headache, the most significant headache in a controlling perspectives and in the stability perspectives. And then comes a problem that is equally severe, and that is related to fatigue. Because even when you use a high-strength steel, you still have the problem of fatigue. Actually, the problem becomes to be more obvious, becomes to be bigger than it is when you use a conventional steel. Why? That I'm going to explain to you later this class. Because I can tell you already why. Because the residual stress is going to be still very high. It's going to be still in an area that when you're loading the structure, you're going to have a plastic deformation, very local plastic deformation, super local plastic deformation. But at the location where the welded joint is located at. So we're going to get back to this and how you can use multi-body models to provide the data for fatigue needs. And this is something that, sometimes it feels that the engineering life is not progressing that well because I made my dissertation, I need to do the math, okay, 27 years back. Oh my God. Oh my God, I should not, that was a big mistake to mention that because I started to feel like, I have a pain in my back. And that was a mistake. Okay, I take it back. Some years back. So now I felt young again. So okay, some years back, I did my doctoral dissertation, and it was all about how to use this multi-body to predict, give it the loadings for fatigue analysis. And surprisingly enough, at the moment we have a project proposal that have been submitted to Business Finland, and it's pending at the moment. We're expecting to get the decision maybe this month, next month latest. And guess what? The subject matter is how to produce loading information for fatigue purposes. So it's pretty much exactly one-to-one what I did a while ago. But different concept. Because at the time, I was able to run things that are like 10 seconds. Big problem because 10 seconds is not much. The fatigue is something that is a statistical thing. You need to use your machine daily basis, day in, day out, week in, week out. And then you can collect the statistical data about the loading. I was unable to do that, but I was able to give a loading, but a very short period of time. What we can do today is that we can get this statistical thing. We can run things faster than in real time or real time if nothing else. And then we have also more advanced fatigue analysis tools. So, but again, we're getting back to this. And why this is now a hot topic is that simply because of the high strength steel. And this is a big trend. In a car, they're already using high strength steel quite a bit. And more clever way, there's a different steel material depending where you look at your car body. I don't know the details of the cars, but that's what I've been learning from the basic magazines. Okay, all right. So that, and then this contact things. We're gonna take a look at how is that the contact modeling can be used in a bearing modeling, how is that can be used in a different things. A little bit of something that takes again a little bit of back in the time, and because the bearing modeling is something that is a quite a hot topic, but contact modeling we're going to use in another application than the bearing modeling too. So something that is going to come later. And that's it. What did I promise? I promised 5 minutes. 5 minutes. I promised 5 minutes. Okay, so what am I saying? You need to divide it by 2 or multiply it by 2. So my story is 2 is a good factor. So I say 5 minutes and it was 10. Okay, all right. Okay, so but now we're going to move on to three-dimensional multi-body system dynamics. Introduction, description of particles, Euler angles, which you already know. And then the main thing is a Rodriguez equation. That's what's going to be the main body of today's lecture. And that's where we're going to close today. Maybe we're going to take a look at the Euler parameters, and that's it. Not more than that. Okay, questions are here. So you don't need to take a picture of anything because these slides will be available in the Moodle database. But these are the questions that are related to three-dimensional multi-body dynamics. And again, nothing but these ones. And there are questions that most probably going to be in the exam paper like gimbal locking. So it's something that is good to be aware of. And there's going to be quite a bit of material about the gimbal locking, you know, angular velocity and other stuff. So every single thing will be covered. All right? So that's how we're going to go. And like I said, I'm not able to step outside of these questions. So if there's 11 questions about this subject matter, then this is an 11 questions, with an exception, of course, that if you want to vote on something out, then it's going to be out. How this looks. It's like these are the 11 questions. And I'm not able to take anything. I cannot change the word. I cannot change anything in these questions. They will be exactly like displayed here. Okay? So I cannot even, how much I like, I cannot put any additional questions here. These are the 11 questions. And once we learn them by hours together, then you're good to go to midterm exam. Okay? How that sounds? All right? We get started from 3D multi-body dynamics. So what kind of system can be analyzed using multi-body system dynamics? We're going to get started that. What the coupled simulation means. This is something that we're going to revisit a bit later, because the coupled simulation is something that we have different engineering disciplines that are combined in one analysis. Hydraulically driven mechanism is a very good example about the coupled system. So we have equations that are describing mechanical components, and we have an equation that are describing hydraulics. And what we're doing is that we're coupling them together. Now, coupling can be accomplished in many different ways. You can use a technique that you put everything in a one big set of equations, and you're solving this one big set of equations, regardless how they are. So this is called monolithic approach. Everything will be solved simultaneously. But you can also use something that is very much in a fashion, which is co-simulation, using one integration scheme for mechanics, another integration scheme for hydraulics, or whatever is your other engineering disciplines, and then you are changing information between these two disciplines. That's what the co-simulation is. Now, co-simulation as a procedure, having a lot of, well, not a lot of, but two different under categories. Categories, how you sharing the information, how often and how well you're sharing the information. So this is, but anyways, the coupled simulation means that you have a different disciplines, actuators typically, and mechanical components, and you are solving them together. That's what it means. Okay, so why rotations are more difficult in spatial than in a planar case? So we get back to this. We get back to this too. And this is just shortly. I'm not going to explain it right because you're going to learn it a bit later. Okay. All right. Remember, multi-body system dynamics is a system that consists of multiple bodies. That's where the name multi-body is coming from. Sometimes it could be just a one moving body. It could be simple like that, but is more advanced. I mean, it makes sense to use multi-body system dynamics when you have a mechanisms that consist of multiple bodies that are coupled together with constraints. And the constraints are mathematical representations of joints. So four-bar mechanism is a good example, and there's pretty much other mechanisms too are good examples. So that's where the multi-body system dynamics is very good at. It can be, yes, it can be used in other cases, like where there is a spring components, spring connections between the bodies, but then there's other methods that may be more efficient, like finite element could be more efficient in that case. But anyways, so multi-body system dynamics is something that consists of multiple bodies. Bodies are connected together via joints. And the big thing is this. In multi-body system dynamics, we do not make any assumption regarding the magnitude of rotation. And remember, in the dynamics, the most often the source of nonlinearity comes from large rotations. Because whatever you have the rotation like this much, then you need to use a trigonometric functions, or you can use another kinematic things too, but just shortly, or if we cut the corners, you can say that we need to use a trigonometric functions, cosine and sine. Those are nonlinear functions. And because of the nonlinear functions, your kinematics will be nonlinear. And because of the nonlinear kinematics, in general, there is no analytical solutions available. So what you need to do is that you need to solve the equation of motion in forward of time. So that's what the multi-body system dynamics is about. That's what you learned last semester. Okay, so it can be used in robotics, mechanism, vehicles, and many other things, including this railroad application too. So it can be used there too. Okay, no thinking needed. That's the beauty of multi-body system dynamics. You're just following the certain steps and you're gonna get the equation of motion automatically. Okay, so now you remember how is a multi-body system dynamics. The way we're describing the kinematics in spatial case is exactly the same that in a planar case. So what we're gonna do is that we're gonna describe a particle with respect to reference coordinate system. And the reference coordinate system is typically the one that is not moving. It is standing still. So it's often called like global coordinate system. You have many different names, but there's a reference coordinate system that is that we are measuring the motion with respect with. That's what it is. Okay, big thing to do here is to describe every single particle with respect to this reference coordinate system. Like we learned last semester, easiest to do so is to use a body reference coordinate system that is attached to body. So if the body translates, the coordinate system will do the same. If the body rotates, the coordinate system will do the same. So it's welded. So it's attached, rigidly attached to body. Always attached, rigidly attached. There's only one exception, and the one exception is related to... Correct. How you knew that?
Actually, you told us last semester.
You were listening to me.
Yeah, why not?
I'm in a shock. So you remember, first of all, you were listening and you still remember. Really? So I need to start paying attention to what I'm saying here. I thought that you guys are thinking, okay, Friday, first time I'm going to go to liquor store, and then I go to, that's what you're thinking. And then you're just looking at the slides, but your thinking is something else. No, not liquor store.
No.
Okay,
Not
all
my
right.
cup of tea.
What was that?
Not my cup of tea.
Okay, all right. Okay. Yeah, so that is the only exception. The formable bodies, there is this method we're going to learn. It's called floating frame reference formulas. As the title implies, in that particular method, this reference coordinate system is floating with the body. This is weird because is it attached or not? And answer is yes and no. It is attached when you're describing the rigid body motion, but when there's a deformation, then it's all of a sudden floating with the body. So it's a de-attached to material point, but it's still traveling with the body. We get back to this, but for now on, you can consider that this is rigidly attached. Okay, so that's how it goes. And then we're going to use the kinematics in such a way that we first describing the vector from origin of the reference coordinate system that goes to the origin of the body reference coordinate system, that's vector R. And then we're going to take the orientation of this coordinate system into account. This is what we learned. So we repeat this equation more than 1 million times last semester. And then with the help of vector U bar, we're going to describe every single particle in the body. Okay, that's how it goes. And the big question, of course, is how is it we can describe this guy? So this is our kinematics. It's going to be very straightforward. R is consisting of 3 components, so no surprises here. Vector U bar, that too is consisting of 3 components because of the 3 axes in our coordinate systems. But this guy, this rotation matrix, that is a challenging. That is a challenging, and it's amazing thing that, math been out there already quite a while, as is the case of body rotations. But still you can see the papers that are dealing with the rotations in a 3-dimensional space. And every now and then you hear that, okay, now there's a revolution of the best way to describe the rotations in 3-dimensional space. And if you go to Amazon.com, you type the rotations and quaternions. Quaternions, by the way, is this method based on the 4 parameters, roughly speaking. You can see a number of books about this subject matter. Like, what the heck? Rotations, and that many books about this subject matter. And that's simply because it's still a complicated thing. It's not at all easy, and it's very important, extremely important. All these mechanisms, they rely on the description of how you can describe the rotations, but airspace application, very important application. An airspace application, they're still looking at the more efficient way to describe the particles. And now when we look at these methods, most of the YouTube videos are actually coming from airspace applications. Airspace is these famous stories about gimbal locking. Kind of straightforward, but still not that easy. Okay, but I was here. So this is our kinematics. And what we're going to focus on is this guy. How to describe the rotations. How to map vector U bar from body reference coordinate system to global coordinate system. Same, absolutely same concept that we learned last semester, but the dimensions are different. But the concept-wise, no difference whatsoever. But the first thing is Euler angles. Explain the concept of Euler angles is a question. Explain the gimbal locking. So it's related to these Euler angles. I think that we discussed this shortly last semester too, so I'm going to be a little bit brief to describe the Euler angles because the main body of today's lecture is Rodriguez equation. And that is a method based on 4 parameters instead of 3. Okay, so it goes like this. It goes like this famous thing about these rotations. And again, I need to test how well you remember these letters. So we're gonna do these rotations by using 3 successive rotations, meaning that there's one rotation after another. That's what the successive means. Okay, so we get started from the configuration that we have 2 coordinate systems that are completely parallel with respect to each other. And then we're going to introduce 3 sets of rotations. Successive rotations. Successive is a key component to understand here. And it goes such the way that the first rotation, first these coordinate systems are parallel, and then we're going to take a hold of the z coordinate axis. And we're going to introduce the rotation amount of phi. Okay, phi, phi. Okay. Doesn't really matter. That's why I never memorize this because, they can, I can call it whatever. It's like a K. It doesn't make any difference. So it is what it is. And you can read this better than I do. Okay. All right. So we have coordinate system that is now once rotated. And then comes the successive part. So we take a hold of one rotated coordinate system, and then we introduce the second rotation that will take a place around z coordinate axis. And then the third one that is going to take a place around the z coordinate axis, and this is psi. 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 So it went correctly. Phi theta psi. So I said it correctly, did I? Pretty correct. Quite correct. Okay, these are the three successive rotations. And like I mentioned earlier, so they probably come from the gyro. So the gyro is the one that is located in upper right corner of this slide. Now what you can do is that each of these pieces of rotation you can describe by using 3x3 rotation matrix. They resemble very much about rotations we learned in the planar case, because upper left corner of the first rotation is exactly the same we learned to use in the case of planar rotation. Lower right corner is same that we learned to use in a planar rotation, and upper left corner is again the same. Successive rotations mathematically can be described by multiplying these matrices together. And when you do so, then you can get your rotation matrix based on Euler angle. And again, I'm going fast here because we learned to use this already last semester. Okay, now I have a method based on 3 rotations. And 3 rotations is something that I've now, the one that I highlighted inside of my representation. Whatever you're using 3 rotation, you're going to have a singularity one way or another. Typical way of singularity is that rotations are not clearly recognizable. It can be the case like when the gyro becomes to be in a certain configuration, then you are not able to recognize, are you going to do the rotation using first or third parameter, because they're going to be having the same axis of rotation. And that's where this Kimball locking is coming from. So the Kimball locking, even though that it says locking, is not the mechanical locking, but it's an inability to differentiate what is what rotation. And this is something that, you can measure that in such the way that you can compute the rank of this rotation matrix. Now, as soon as you see that the rank is as soon as the rank is started to change, you know that you're approaching this locking configuration. And in software configuration, the commercial softwares can handle it in a way that they can start adding artificial angle to one of the coordinate axes. And this is the way that they can get rid of it. But still, is a fundamental problem that you cannot solve if you use 3 parameters. So you always have this problematic case is that these rotations are not clearly recognizable, or it may be the case that certain components, if you use a completely different representation rotation matrix, certain components could be like infinite divided by infinite, which you cannot compute it. So it becomes to be mathematically singular. But singularity is the problem whatever you're using 3 parameters. This is coming from the fact that, this is my first lecture, I realized that I forget some of the stuff to my home office, including my pen. So we'll see if I'm able to do the writing using my finger, because something that I wanted to explain to you. Oh. Okay, we'll see. No. Absolutely not. Let's try this. But is this a risk too high to take?
We'll just take a look at this and then tell you.
Okay. So now you're going to see what's behind the curtain.
Yeah.
Okay, no good.
You have to move it.
Okay. Just. Yeah, that's an Apple. That's not going to work. Yeah, that's a. Thank you, but that's because it's another kind of the electrical pen. Okay, you guys. I'm going to just take this off a little bit, and then I'm going to write this, because what I'm going to write is very simple thing. Is this. angular velocity. Oh, you don't see it. Okay, I'm gonna. Okay, the online participants cannot see it.
No.
No. Okay, careful with that, not to fall it down. Okay, no. Angular velocity. Now it's gonna be visible, isn't it? Yeah, it is visible. It starts.
Like start from here.
Okay, there. Okay, angular velocity. Okay, I have this. This is my coordinate system. Angular velocity is something that is measuring the velocity around this axis. Okay, so angular velocity as a vector, this is a 1, this is a 1, 2, 3. Okay, all right. Okay, so here's what I'm going to do, because we only have 15 minutes and we still need to go the Rodriguez equation. I'm going to just explain it. Okay, let's put the curtains back. No. Because it's not in my office, my university office, but my basement office. And cycling back to my basement office is going to take an hour. Okay, so.
Is it okay if I turn this a bit around because you were most of the time visible in the...
Okay, sure, of course. Okay. I'm going to say it. So the problem is that, when you differentiate, you can see my pointer here. When you differentiate these rotational parameters, that's not the same than angular velocity. Regardless how you do this selection, regardless how you do this more, here. Now it's too much because of the delay. Because I see that the camera is pointing. Okay, all right. So when you differentiate these rotational parameters, they're never going to be the same than angular velocity vector. Never. You need to map them one way or another. This just shows that the problem. And I know that you hear me like, differential, it's okay, because we're going to look at this again next week. And we're going to look at this, okay, what it actually matters. It's a seemingly very simple concept, but it makes life difficult. And the easiest way to fix this problem is that introduce one additional parameter. And this is against the common sense. Because if the body can rotate in 3 different ways, then we should use 3 parameters, right? But now what I wanted to do is that instead of using 3 parameters, I want to use 4 parameters because it helps me. Then I'm not going to suffer anymore about the lockings. I don't suffer anymore about the singularities. So it's mathematically more pleasant. Human common sense-wise is against that because human, if I give you 4 parameters and saying, okay, how is the body orientation? No one would understand the body orientation. The computer can, but the human brains cannot. But the computer computing typically is based on 4 parameters. Most of the cases it's such that the user interface may be made such the way that there's 3 parameters. But as soon as you start the engine, as soon as you started dissolving things, then it switched to the 4 parameters because that's what the computer is so much more clever with. Okay, so it's gonna go like, okay, first of all, the story about the Kimball locking is this inability to understand what is what. And I want you to take a look at the following videos. There are several videos about how is a gimbal locking. They're pretty good, actually. I'm not going to play it today, but I'm going to give you a link. So please take a look at them. Each 3 to 5 minutes max. So they are not longer than that. And then the best one about the gimbal locking is, there's one more. And this one, I think it is the best. This lady is telling the story about Apollo 13 and gimbal locking. So take a look at that. So I'm going to make you a list of YouTube videos. So please take a look at them. All right? We're going to continue to discuss next week, Wednesday. So I'm rushing here a little bit because the main body I keep on telling that the main body of today's lecture is a Rodriguez equation. And it seems that that's going away because 15 minutes left. Okay, let's move on to that. Okay, we get back to this. Take a look at this. I'm going to ask this exactly same in-class quiz. The in-class quiz is not on at the moment. When using three rotational parameters, the problem is singularity, physical interpretation of parameters, usage of three parameters is limited to small rotations only. What is the correct one? Singularity. Singularity. This exactly same in-class quiz will come next week, Wednesday. Exactly same options. And do you think we're going to score 100%? No. No, because something is broken in our system. Something is seriously broken. Now, that's why I was thinking that you listen to me, because whatever I'm telling, we're never scoring 100%. So that's why I was thinking that you have this liquor store, then party, then I will go to this and that. And
Problem is the singularity.
yeah, well put. Yeah, the problem is singularity. Okay, so we get back to this. Rodriguez sequence, and this is really important. Okay, explain the concept of Rodriguez equation, explain the concept of Euler parameters, and then we get back to this third question. What is this concept? And the concept goes such the way that we need to go and take a look at the math. And in the math, I'm going to introduce you a vector. And the vector is the one that is this vector r here. And what I'm going to do for this vector r is that I'm going to introduce a rotation. Well, let me get back to this. Let me get started again. So this is your vector r. And then you're going to introduce a unit length vector, which is a vector v. This vector here is small because it's a unit in the length. I'm going to attach this unit length vector to certain point, the origin of my vector r. And then I'm going to introduce the rotation in a completely different way that I did in the case of Euler angles. So I'm going to introduce the rotation in such the way that I will take a hold. And first of all, I'm going to weld these two vectors together. So they're having this configuration like this. And then I'm just going to take a hold of my unit vector v. And I'm introducing the rotation like this. Then, what is left me to do is to define where this vector r is in the beginning and where it is at the very end. And this change from here to here will be described by using rotation matrix. This rotation matrix will be based on following parameters. Vector v, it's going to give you how many parameters? 3, because it's a spatial case. So this you need to define by using 3 parameters. And the last parameter is going to be amount of rotation. Those are going to be your 4 parameters. That's it. You see already that this is usability of 4 parameters is not pleasant, because how much it makes sense for human brains to understand this kind of the stuff about the unit vector and rotation 0. It's very, very complicated to understand. But this will introduce us a Rodriguez equation that will not suffer from singularity. Regardless of the configuration, it's always able to give you the clear answer, what is a configuration. It's never get confused about axes or anything like that. So that's the beauty of it. Okay, so what we need to do is that we need to go and take a look at a little bit about the math behind. So we need to create the relation from the original configuration and rotated configuration of vector r. And it's going to be a bit involving. So we need to use assisting vectors, b1, b2, using the trigonometrics quite a bit. Actually, not just a little bit, but quite a bit. We need to find a direction. We need to find a length. Using these 2 pieces of information, we can finally define them. And using then these B1, P2, we can figure out how is the relation between original and final configuration of vector r. Okay, here it goes. Take a breath, really breathe deeply. one more time. And now it comes. Okay. I'm cutting corners quite a bit. So I have here this delta R that is representing this one here. So when you're moving from here to here, and this is how you can describe the vector delta R. This is going to be eventually our rotation matrix. And like I say here, this is going to be based on the P1 and P2. If you want to learn the details of P1 and P2, I have them too. But I'm hoping not to take a too close look about that because it's a mechanical math. And again, you can use a symbolic math tool to figure it out. So you can figure out the length of B1. You can figure out the direction. It's just the trigonometrics you use here. And then you can use, you can get the B1 and you can do the same for B2. Again, length and the direction. It's quite a bit of cross product. So it's going to be a bit involving. So a little bit involving, but this is how it looked like. This is how it finally looked like. And then getting back to the slide that I get started, this is how is a delta R. Oh, one more thing that I forget to mention. In math, the cross product can be replaced by another denotation, which is very often used in kinematics. And this other notation that is very often used in kinematics is the skew-symmetric matrix representation. Have you ever heard that before? That's okay. It goes in this way. You have here a cross product of vector R and vector B. This is what you have. I'm sure that you learned this already in junior high school. Okay? Okay, so and you can do the cross product like shown here. So you're taking the corresponding components from vector A and B, you multiply them, and then you subtract them from each other, and that's how you're gonna get the first component, second component, and third component. This is a basic math. Same solution you can get by not using this kind of like predefined computing, but using matrix and a vector. So what you can do is that you can describe this first vector, which is a vector, by a matrix. And this is called skew-symmetric matrix. It's again something that you just take a component of vector R and you relocate them as it is shown in this matrix here. You take a first component, you located that to be here in a minus sign and here as a plus sign. You take a second component, you put it here, and the third component, minus sign here and here. So when you look at the diagonal of the matrix, it's going to be 0, but off-diagonal components are non-zero. What's the benefit? It's the benefit that now when you, so I mean that you can just replace this cross product by a matrix and a vector. Later in a manipulation, it's very, very handy to use it because then changing the order of cross products is going to be simple to do it, and that's going to be something very beneficial. This is called skew-symmetric matrix. And you can form it from vector mechanically. Okay, back to this. So this is my rotation matrix, and now when I use this skew-symmetric representation, I can finally express my rotation matrix like shown here. Okay, first one here. Let me try to use this one such that the online participant can see this well. So this is identity matrix. So it's a 3x3 matrix where the diagonal components are 1s, others are 0s. Then comes vector V. The vector V is placed in a skew-symmetric form. So it's a 3x3 matrix where the components are occupied, off-diagonal components are occupied by components of vector V. Very simple. And then comes sine, angle, theta. And the angle theta is the amount of rotation we did in the very beginning. Then comes 2 multiplied by skew-symmetric matrix power 2, and then multiplied by sine 2 power 2 cosine divided by 2. Okay, like I say, I have 4 parameters in this notation. First three ones are related to vector v, and the fourth is the one that is related to angle theta. Now, these must be somehow combined. There have to be a relation between these four parameters. Why? Because the body can rotate only in three different ways. So it's not possible that these four parameters are independent. They must be combined by constraint equation one way or another. Now, what is the way that they are combined? How they are related to each other? Because they're having a relation. They are cousins. Not cousins, they're having the relation. So how is their relation? What is the one that makes them to be not independent but dependent on each other? The welding, that they're welded together? Oh, you're getting close. You're very, very close. Very close. But it's not exactly the right answer.
Because we can actually, it's not that we can use actually a welding joint. Maybe we can tell it as something like a bearing joint.
Okay, so it's getting close. But yes.
The angle?
And angle between them. Okay, you guys are very, very close. You're very close. Remember, the vector v is a unit in the length. So that's the answer. Unit. Unit. Because it's